Hi, let's take a look at, let's talk about equilibrium today, okay? When an object is in equilibrium, it basically means that the sum of its forces will balance out. So what do I mean by that? Let's look at, there are two cases. The first case is dynamic equilibrium. The other case is static equilibrium. So when you say dynamic equilibrium, okay, you are saying that the sum of the forces will be the same, will be equals to the mass times acceleration. Okay, therefore if you look at this, sum of forces equals to mass times acceleration. This means that the traction, which is the force that comes from the engine, the traction force minus the friction force that is created from the ground onto the car, okay, will give you the acceleration times the mass of the car. Okay, so T minus F is equals to ma. For static equilibrium, you are saying that the sum of the forces will eventually become equals to 0. Why? Because it's not moving, no acceleration. Okay, so sum of F equals to 0. So in this case, you have weight and the reaction from the ground. Both are opposite direction, so one has to be negative of the other. Okay, if we pick upwards to be positive, so W will be negative. Okay, so R minus W is equals to 0, so R is equals to W. Okay, so this is your static equilibrium. Okay, let's focus this time, let's focus on static equilibrium, okay, because it's easier to visualize. Here are some examples. Okay, the first one, you have the guy whose weight will balance out by the reaction that the ground is acting on him. So in this case, the object is the person. Okay, the object that you look at. You're always looking at one object, the forces acting on the object. Okay, for the second case, the object is the shaft. Okay, you are the shaft. What forces are you experiencing? All right, so if I add a torque, a twisting force at one end, the wall will give you a reaction torque at the other end. Okay, and this torque will balance out with the reaction torque. Okay, so this is also static equilibrium because it's not moving anywhere. All right, and the third case is the beam. If you have a horizontal beam and there's a point force acting in the middle of the beam, you're gonna have two reactions at the support ends. Okay, so these will also be in equilibrium. The downward force will be balanced out by the two reaction forces. Okay, and last but not least, imagine a guy who's trying very hard to push a block but not able to push it, but it's still stationary. It means this block, the object is the block, is in equilibrium. Okay, but what forces are acting on this object? You have the weight, the reaction force by the weight. Okay, although it's not moving, the guy is still pushing. Okay, and that is the pushing force here, which will be balanced out by the friction. Okay, that's caused by the surface. Okay, the surface of the ground. So these two will also balance out. So eventually, if you have a static equilibrium, you can say that the sum of forces equals to 0. And one more thing that is not so much mentioned just now is that the sum of moments is also 0. Okay, if you take moments about any point, okay, it will also end up in 0. So that is your static equilibrium. Now, I'm going to talk about a very interesting case here because I feel this one may give you an easier visualization. Okay, you have three persons. Okay, there's one guy in the middle who's holding hand on to the left and the right guy. The left and right guy are pivoting on their foot. Okay, on one foot, and they are pulling the guy in the center. The question is, are they in equilibrium? Yes, they are, because they are not moving. They are there. They are able to hold on to their position. So then they are in static equilibrium. Okay, in fact, you can treat these three guys as one single system, one single object, okay, which has the combined total of all their weights. So this whole system has a weight of the three persons, and there will be a reaction force that is equivalent to this 3 persons weight from the ground back onto this 3 person. Okay, so this is in equilibrium, and the so-called object is 3 person. Okay, now if you are the guy on the left, okay, then I want to ask you, are you in equilibrium? If you are the person, if there's one person there, you're not part of, you're only part of this whole system, but you are that one person. Are you in static equilibrium? You will say yes, right? Because you are not moving, you're balancing yourself out. Okay, you're not falling, you're balanced, so you're in static equilibrium. Then how do you visualize the forces on you? Okay, this is how you should see it. Okay, you have your weight somewhere around your center of gravity. I would say somewhere around here you have your weight, and because of this weight you're going to have a reaction created from the ground onto your foot, which you are pivoting. Okay, and in addition you're going to feel the tension that is from the middle guy pulling your hand. So this is a force that you're experiencing, okay, because you are the object, you alone are the object, and this is the force that is being applied on you. Okay, and also you are experiencing a frictional force from the surface. So in actual fact you are in static equilibrium. Okay, your friction will balance out with the pulling force. The reaction will balance out with your weight. Okay, so if even without looking at the whole system, okay, but by looking at one part of the system, this part will still be in equilibrium. Okay, and if you look at the other part of the system, which means the other two guys, are they in equilibrium? Yes, they are. Then how do you draw the forces? You're going to have the weight of the two people, and the force is going to provide the reaction caused by these two people's weight. Okay, and the center guy is going to feel a pulling force from you. Okay, so there is a pulling force here. Okay, and because of that you also have a friction force applied onto the whole system, that is the 2 person. Okay, so overall they will balance out. T will balance out with F, W will balance out with R. Okay, so by breaking up in the system, by breaking up the original system, okay, into 2 separate systems, these 2 systems will still be in equilibrium within that, among itself. Okay, and notice that before that there is no friction, there is no pulling, right? But once you break it up, you will encounter a pair and opposite. Okay, a pair of forces but in the opposite direction. Okay, you see this is at the pulling force, the pulling of the hand, and this is by the friction on the ground. This pair will be equal and opposite. Okay, in fact, if you combine them back, if you combine both back into one single system, they will cancel out each other, and you will go back to this one single system where you will no longer see the pulling force, you will no longer see the friction force. Okay, yeah, so that is the gist of it, in trying to tell you that if you split up the system, each of them will still balance out. Okay, and this is an illustration of the working, okay, of one person. Let's say he is a 60 kilogram weight. Okay, so he's 60 kilogram mass, so his weight is going to be 60 times g, okay, 9.81. all right, so vertical forces balance out, your reaction is going to be 60 g as well. Okay, like I mentioned, one thing we did not talk about is the sum of moments equals to 0. If I take the pivoting point, okay, and I take moment about this pivot point, what moments do I have? Okay, I will have one that is caused by the pulling force, okay, and the moment arm is 1.5. okay, This is an arbitrary figure, and the distance between the pivot point and the center of gravity is, let's say, 15 cm, okay, which is 0.15 meters. You can see that, okay, by taking moments about the pivot, you can identify that the pulling force is in fact, okay, 6 times g. Okay, 6 times g Newton, because I have one moment that is clockwise caused by the pulling force, and another moment caused by the CG, the weight, which is anti-clockwise. So I can take clockwise be positive, anti-clockwise be negative, and you can find the pulling force T. Okay, and by summation of forces in the horizontal direction, okay, which will balance out, right? So you'll find that the friction is also 6g, and you know that the friction is equals to the frictional coefficient multiplied by the reaction. You can find that the friction coefficient is actually 0.1. Okay, so this is an illustration of using the equilibrium forces, okay, on just one part of the whole system. Okay. In fact, I also want to tell you, this is a reinforcement section. When I say sum of forces, sorry, when I say sum of moment equals to 0, okay, you can literally take any point and you take moment about any point. If this person is in equilibrium, the sum of the moment at any point will be equal to 0. Okay, so this is an example. If now, instead of taking the moment about the pivot point, right, which I just did just now, I take moment about the center of gravity. Okay, I take moment about center of gravity. You will find out that they do really cancel out each other. Okay, so this is the equation. The moments about the center of gravity will be one caused by the pulling force, and this time the moment arm, let's say this is x, a distance x, okay, a vertical distance x, and the other moment is caused by the friction, okay, and the moment arm is 1.5 minus x. Okay, so the equation will cancel itself out. You actually do not need to find what the value of x, because they will cancel out. Okay, and you also realize cancel out that the other parts will also cancel out, so they are in equilibrium. Okay, so this is an illustration that you can take moment about any point of the object. It will always be equal to 0 if it is in equilibrium. Okay, now let's look at something more relevant to you. Let's look at the beam. Okay, shear force bending moment. Okay, shear force bending moment is actually the internal forces. Okay, that pulling force between the hands. Let's look at it. Suppose you have a beam, right, and the point load is here, and you have two reaction forces. If you cut any part, let's say I cut this section over here, okay, and you look at the left hand side of the beam, okay, you're going to see this is its own system, and this in fact is in equilibrium. You can do your sum of forces equals to 0. You can do your sum of moment equals to 0. Okay, and like what is happening to the three guys, you're going to have a pair of forces and moments that will appear. Okay, that will appear, so that when you combine them back, they will negate each other, because this is anti-clockwise, this is clockwise, right? So when you combine them back, they will negate each other. This is downwards, this is upwards, so they will cancel out, and you go back to this configuration. Okay, so after you break them up, these two will come out to balance out the system. And if you look at the other side of the beam, this will also balance out with the whole with the rest of the forces and the moments. Okay. And a very simple example. Okay, I give some numbers here. 2-meter beam, the point load is 10 newtons. Okay, so the reaction naturally, since it is at a dead center, right? So these two reactions will be same, 5 newton each. Okay, I'm going to break this beam at the 0.5 meter part. Okay, and let's look at what happened. Okay, I section this out. I look at the left hand side. This is the free body diagram of the left section. Okay, I can say that the sum of forces in the vertical direction is the same. It means that my shear force will be 5 newton. Okay, I can also say that sum of moments equals to 0. So if I sum moment of about, let's say at this point of cut here, I sum moment here, I get M, which is that pair of internal moments, M minus the moment caused by the 5 newton, because M is anti-clockwise, this moment is clockwise, so they have to be opposite sign. So you will M minus 0.5 times the moment arm is 0.5, okay, times the force is 5. So your bending moment is 2.5 Newton meter. Okay, if I look at the other side, okay, if you look at the other side and you do the sum of forces and moments as well, you will find that indeed the F, you can calculate it to be 5. Okay, this 5 means that this direction that I draw is correct, is upwards. Okay, I'm going to tell you is here, if I draw the force upwards and I sum of forces equals 0 and I treat the upward force as positive, so I will have F is positive, 5 is positive, but only the 10 is negative. Okay, so F I will find out to be 5 Newton, which means this F 5 Newton is going upwards. Okay, if in any case I find the F to be negative, it only means that the arrow that I draw, the correct direction is opposite, is downwards. Alright. Okay, so this is correct, upward force of 5 Newton. This is my conclusion. Okay, same applies to the sum of moments. At this point, at the point of cut, I find out that my moment is 2.5. Okay, this is a positive value, 2.5. This means that the clockwise moment is correct. Direction is clockwise. Okay, if I ever find the moment is negative, it means that the arrow that I draw, the correct direction should be opposite. Okay, so for this case is correct, it is the clockwise direction. Okay, so you look at the two forces that you find and you look at the two moments that you find. Okay, and you look at the direction, one is indeed opposite of the other, this is indeed opposite of the other. When you combine them back, these two pair of forces will disappear. Okay, and you will return to the original whole system. Okay, so this video is to illustrate to you that in static equilibrium, what we mean is your vertical forces, sum of vertical forces is 0, sum of horizontal forces is 0, sum of moments at any point of the object is 0. Okay, and this can apply to the whole system, okay, or just part of the system, as long as they are in equilibrium. Okay, and the sections of a system, for example this, if I section them out and look at them individually, will reveal pairs of equal but opposite forces and moments. Okay, equal pair but opposite in direction. Okay, and the section of the system is still in equilibrium, like I say. and you can always apply these equations onto one section, okay? Or I use this as an illustration. You can always apply the sum of forces equals 0, sum of moment equals 0 for each of the individual section. Okay, and so this is the what I'm trying to explain to you, to show you the meaning of static equilibrium.